Well, hello, NATR 346. This is a quick talk to introduce you to a homework assignment mapping exercise. We're going to be mapping salinity in the Delta region, salinity of surface water quality in the Delta region. So in Module 6, Water Quality Basics, you'll see there's an introduction to water quality and some 3 talks there that are important to go over prior to doing this exercise. But here we have the homework assignment, salinity mapping in the Delta. And if you go there, you'll find 4 files. I want to introduce this concept in general. This is just a 2-page explanation of what we're talking about here. And we're talking about maximum salinity intrusion in the Delta. So I hope you recognize this map as a map of the San Joaquin Delta. Here's the McCullamy River and the San Joaquin River. Here's Manteca and Stockton. And all these drainages that come together and form the Delta. And primarily the drainages are the San Joaquin River and the Sacramento River. And they combine and head out the Carquinez Strait out to the Pacific Ocean. So this delta, we'll get into the delta in a lot more detail in another unit, but for now, it's important to understand that, when there's a lot of rainfall and fresh water flowing through all these drainages, it tends to push the fresh water pushes the saline water out. And alternatively, when we have a drought, we're damming up our rivers and we don't have a lot of fresh water moving through the system, the saline water will intrude. And this is very undesirable. We have a lot of agriculture out here, and farmers do not like salty water to irrigate their crops. And what this 2-page little mini article does is it compares the maximum salinity intrusion that occurred in olden days between 1921 and 1943 to current times, 1944 to 1990, more current. And the point here is that when we built the Shasta Dam and the Central Valley Project, it allowed us to trap fresh water and in the summertime release that fresh water and push the saline water out to prevent it from intruding. So here's before the Central Valley Project. You can see saline water. Here's 1934. This is a line that demarcates. Here's 1931. Back in 1931, this black line was the contour of water quality. So in 1931, if you were on this inland side of the contour line, it was fresh water. If you're on the west side of it, it was seawater. Back in 1938, this line was all the way out here. So that was a wetter year. The fresh water pushed out here in 1938. So in 1938, if you were in Pittsburgh, you would have pretty much saline water, salty water. But all here on the other side of this contour, you had fresh water. So there was a definite problem that prior to building the Central Valley Project and all the dams that we used to flush fresh water through the system, you would get saline water coming way into the Delta. And here in 1931, if you were a farmer here in Cortland, you were pulling water out of these rivers and it was salty and they were not happy about it. That was the condition from 1921 to 1943. After 43 and the dams were built, you see what happens to all these annual contour lines. They kind of bunch up. The worst condition that we had looks like 1977 or so, maybe 1944, where seawater came in all the way into this island here. But again, the way to interpret these lines is to the right of the line is fresh water. To the left of the line is salt water. And the exercise that we're going to do for this homework assignment is to draw one of these lines with real data. So the first thing to learn, if you haven't experienced this already, is the concept of contouring data. And the idea is you want to draw a line of equal, that shows equal value. So let's say you don't know what these numbers mean. It's 1, 2, 3, 4, 5. They're just numbers. But you are interested in knowing where to find the value of 3.5. Again, not saying what it means at all, but here's 4 and here's 3. So 3.5 is in between 3 and 4. Here's a 5 and a 4. Well, there's no 3.5 there. We go, oh, here's a 3.5. Must be somewhere between 3 and 4. 2 and 3, it can't be here. Here's a 3 and a 4. So you just find the 3.5. If I can get this comment to work here. Yeah. So you go in between the 3 and the 4, and here it is. You go between the 3 and the 4, and here it is. 3 and the 4, here it is. And you just kind of cruise around like this. And so now you know, after you drew this line, that everything up here is greater than 3.5. It's either 3.6, 4, 5, always on this side of the red line, it's greater than 3.5. On this side of the red line, it's less than 3.5. It's either 3, 2, 1, something less than 3.5. That, in a crash course, in a nutshell, is how to contour data. So what we're going to do for this exercise, you're going to love it, trust me, is this is a real map of the delta, and these red dots are monitoring stations. They're stationary. They use them year after year after year, and they measure the electrical conductivity of the water. And if you read that paper on salinity and or listened to the talk about salinity, you know that electrical conductivity is the measure of how salty the water is. If it's got a lot of salt in it, it can conduct electricity really well. If it's deionized water, it can't. So it's a measure of how salty is the water. And so we saw these contour maps of the past, drawing that line of where the water is salty and where it isn't each year. And they drew these lines by contouring conductivity data from these stations. And so the goal here is to, for September 24th, 2016, what was the salinity of the water at these stations? Step 1 is to plot that. And then step 2 is to contour the 1,000 conductivity contour line. So where you get the data is from this stack of conductivity data. Each of these graphs show, here's the date and the time at the bottom, and on the y-axis is the microsiemens per centimeter. That's just a measure of how conductive the water is. And so for each station, this one is Ryer Island, RYI, September 24th. You go up the September 24th line, bing, you hit this measurement here, you go across, and you just say, well, that looks like it's somewhere around 160, between 160 and 162. We don't need to be precise here. September 24th, conductivity looks like 162 or so, right? September 24th, go up, go across, 162. So that's RYI. So you find RYI on here and plot that value. Here it is. RYI is 162. I like to use Acrobat here, so you can do a comment and put in a text box and say RYI is 162. So that's step 1. I already plotted Grizzly Island. It's 15,000. So you can see that as you go further west toward the Pacific Ocean, the conductivity increases up to 15,000 here. When you go way inland, it goes down to the hundreds. I plotted this one here, SSI, is 4,000. So you can just see as you go out to sea, the water gets saltier and saltier, no surprise. But we're going to dig into that a little bit more. So I'd like you to, for each of these stations, find that station in this stack of charts. Notice how much it varies over the course of a day, but just pick the value that you can find right there on the September 24th line. Don't worry about the exactness of it. Here's SSI, Sherman Island, for example. September 24th, you move on up, head over. Okay, 4250, done. Just put it down. That was Sherman Island SSI, 4250. Hope you can see that. So then you're going to get a bunch of numbers, just like you had numbers on this little kid's diagram. But instead of looking between 3 and 4 to find 3.5, what you're going to do is look for between greater than 1,000 and less than 1,000 to find that 1,000 value. So you know that here's 15,000, you're moving in, here's 4,000. There's no one, all this is greater than 1,000 then. And I'll bet you when you plot these should be greater than 4,000 probably. So your 1,000 line is not out here. Here's 450, so okay, this is less than 1,000. That's greater than 1,000. Your 1,000 line should be somewhere in here. And when you plot the numbers here, hopefully that will help. Here's 160, so okay, that's way below 1,000. So your 1,000 must be out here. Wait a minute, here's 4,000, here's 100. So somewhere between 4,000 and somewhere between 100 is the 1,000 line. And just go ahead and sketch it out as best you can. You'll draw some line through here. I don't even frankly know what it'll look like, but it'll probably look something like one of these historical lines. Maybe it'll look like the line, I'm going to ask you which date most resembles your 1,000 line. Here's the 1926 line. Kind of cruises along through that. So I hope that's clear. Don't worry about details. Please, plot the data and draw the 1,000 line on this map. Excuse me. I think it's pretty easy to use Acrobat. I think most people have Acrobat, and you could just go to comment and then get your line out and go ahead and draw it wherever you think it is. It isn't here. Hint. Again, if this is supposed to be 1,000, here we are at 4,000 here and 15,000 here. There's no way that this is the 1,000 line. The 1,000 line has to be on this side of this 4,000 and on the other side of the 450. See how close you can get it to move through here and see how you do. All right, hope that's clear enough.